Nope. Well, I'm sorry to break it to you, but today you're gonna have to. Because that's exactly what we're about to do. Ladies and gentlemen, welcome to Paranormal Entities. This is the second horror game of the day for the channel. And I'm not doing it out of free will. I'm not doing this because I want to, because it's fun, because it's not. I'm only doing it because on the cable network. So this is kind of a big deal. If nothing happens, we will get rewarded $500 for our time. If we manage to get some amazing footage with our video camera, then we will get $2,500. I still wouldn't do it. But unfortunately, we're rated number 2. So we gotta do it. So sit back, relax, try and chill. And let's do this.
All right, Cliff, welcome to the St. Augustine's Asylum for the Mentally Ill. My producer Tom said good things about you. In your backpack is a flashlight, a voice recorder, an EMF, and a couple of little fun occult things. We'll let you know when to take those out. Ready to pay off some of those college debts and beer tabs? Well, of course you are. And when you're ready, enter in through those front doors.
Okay, so let's just talk about this real quick. Listen, I found this game on Reddit. I saw like 4 or 5 screenshots. It looked good, but I didn't know it was like, I don't know if it's because I'm playing on 4K or this looks intense. I don't know exactly how bad things are at home, Cliff, but you shouldn't have come here. Okay, for $500, I wouldn't do this for $1 million. I honestly wouldn't. Real life, fuck that. No. You don't play with the mentally ill and paranormal activities. Listen, those are things you know it's serious when you've got a big fat Jesus hanging from a cross. Not big and fat, Jesus is not, you know what I mean. It's a big freaking Jesus Christ right there. And that is typically, I love Jesus, okay? But I'm just saying, that is typically not a good sign in video games or in whatsoever. I'm sorry. This is just not. Oh God. Oh God. What is going on here?
Oh, nice. The door was unlocked. It can get a little sticky sometimes. So here's the story of St. Augustine's Asylum for the Mentally Ill. It was founded in the 1880s, closed in the 1960s, and a lot of nasty stuff happened here. I mean, this place is only supposed to house around 500 patients, but at its peak, it was around 3,300 patients in here. I mean, the place was, less of a hospital and more of a place where you dropped your problems off and hoped they disappeared.
Okay. Why, thank you, sir. I appreciate it. What is this?
In the end, this place was sort of against what the Bible's supposed to teach. I mean, there was no love here, no grace, no healing. The patients were not here to be rehabilitated. Ordinary people just wanted them gone from public. They shoved those with non-threatening mental conditions or those deemed inappropriate to society together with legitimate psychopaths and murderers and other violent monsters and basically said, let God sort it out. The atrocities in here are just too much to count. The death toll was unreal. The violence. This is where the 100 hallways patients would convene, and we heard that the patients pre-1920 never actually received decent care. Then the war hit, the depression hit, and then the budgets all fell apart. The room you stand in once healed 20 patients in need of attention, and by the end, 150 patients would pass through.
Bro, this game is creepy as shit.
Starving, attacking each other at random, flaying themselves with metal wires from their beds. Be careful where you step.
Yeah, bro, this dialogue is intense. This dialogue is really good, and it's just giving the overall vibe a very effective touch, to say the very least. Now, I know I see an arrow there, but that is where the devil himself will be. I've got to be very careful.
Alright, this is a good place to start. I want you to take out your voice recorder, and I'll hopefully be able to awaken this place. Okay, spirits of St. Augustine, please reveal your presence to us. Show us that you are in this room. Feel free to interact with anything or speak to us. Use your words, use your voice, and let us know that you're here.
Are you fucking insane?
Okay, play that back.
Are you
know that you're here.
I'm sorry, this is fucking loud in my ear.
Nothing. Alright, let's try it again.
Guys, this is super loud. So, like, if I jump out of dumb things, just understand this is loud as shit. Okay, I'm standing right here, dude.
Alright, let's try this. Ghosts of St. Augustine, please let us know that you are still in this hospital. I give you permission to reveal yourself. I give you permission to come to life. Just give us a sign that you're here. Tell us where you are. Speak to us now into this microphone. Alright, check that. Now into this microphone.
Oh, God.
Alright, let's try one more spot.
Oh, God. Oh, God. Oh, God. This was a terrible idea. It's too freaking late to be playing this, man. Oh, God.
Ghosts of St. Augustine, you're all a bunch of ghoulish pricks. Show up or piss off.
Ah! Fuck you, stupid fuck! What the fuck is your problem, asshole?
Whoa, did you hear that? Play that back, Pricks, show up or piss off.
Holy freaking flippity flop!
Oh,
this guy's an asshole.
Alright, looks like we got an investigation. Alright, I want you to go down the morgue hallway, and we're gonna continue our investigation in the other gathering area.
Oh, oh, dude, I was not expecting that. Listen, they said the jump scares were insane. But I'm sorry, I just gotta hydrate. I'm gonna die.
More than 20 years ago, a team at Brookhaven National Lab detected a missing piece in the Standard Model, a measurement they had taken to better understand the effects of the forces that shape our universe was off. So the international physics community came up with a plan. Take the measurement again with much more powerful instruments and see what sticks. Fast forward to April 7th, 2021, that
what would happen if you fell into a black hole? If you'd asked Albert Einstein, he would have told you that according to his general theory of relativity, you'd be sucked into the black hole's singularity, the point where space-time curves steeply inward and all the laws of physics seem to break down. After that, nothing can escape. In the 1970s, Stephen Hawking took a semi-classical approach to black holes. Bringing together quantum theory and Einstein's relativity, he proved that black holes emit a small amount of heat that eventually causes the black hole to evaporate. Still, according to Hawking, if you fell into a black hole, you and your particles would be lost to the universe forever. This is Don Page. He was a postdoc with Stephen Hawking, where they became friends, despite the fact that they ultimately landed on either side of one of the most controversial debates in modern physics.
I looked at Hawking's argument and I became not convinced by it.
Hawking's work implied that black holes violated a central principle of quantum mechanics called unitarity, which says that the present always preserves information about the past. So how could it be possible that black holes destroy information. This became known as the black hole information paradox, and for decades, it made physicists queasy. According to Page, if you were to fall into a black hole, you wouldn't be gone for good. Particle by particle, the information needed to reconstitute your body would reemerge.
Well, it would be highly scrambled by the black hole. It'd be much worse than even, if you just cremated the body and it turned into smoke and ashes. But, another analogy is if you burn up a book and you have all the ashes, the information is still somewhere there, is somewhere in the universe, we believe.
The key to understanding why the information is preserved lies in a process called quantum entanglement. When black holes emit radiation, that radiation maintains a quantum mechanical link to its place of origin. If you tried to measure the radiation or the black hole separately, the information would look random. But when you look at them together, they exhibit a pattern.
If somebody took a coin and cut it in half, and then you sort of shook it up and put it in two envelopes and sent it off to two people, then of course there would be what we call correlations in it. If one person gets a head, the other person would have tails. And this quantum entanglement is like that, except it's an even more subtle.
This is the Page curve, which he created to track changes in the entanglement between a black hole and its radiation as it ages. The degree to which the information is entangled is called its entanglement entropy. At the start of a black hole's life, its entanglement entropy is 0, since it hasn't emitted any radiation. And at the end, its entanglement entropy is 0 again, since the black hole has evaporated. But in between, as radiation trickles out, the entanglement entropy grows. Page showed that, in theory, information can escape from a black hole. In a series of groundbreaking papers, physicists have shown that In a series of groundbreaking papers, physicists have shown that the entanglement entropy of black holes really does follow the Page curve.
These calculations give more evidence that indeed the information does come out, but the details of how that actually happens and still remain to be understood. And of course it raises the picture that maybe space-time itself is not fundamental. Maybe there's something deeper than space-time, and maybe the basic quantum description will involve something that's not space and time. So I think there'll be parts of the puzzle, I think, that'll persist for many more decades.
Another puzzle that's baffled the scientific community for decades is superconductivity. When various solids are cooled to extremely low temperatures, they can conduct electricity without losing energy. This happens because the freezing temperature allows electrons to move slowly enough to overcome their natural repulsion with each other, and they begin to form pairs. Like any good couple should, they balance each other out and begin to move in the same direction. When this happens, electrical resistance disappears. This is what makes superconductivity the holy grail of energy efficiency, if only scientists could overcome the limitations of temperature. This is Ranga Dias. This year, he and a team at the University of Rochester created a metallic compound that for the first time exhibited superconductivity at room temperature.
So you have a very small two diamond tips that's sitting opposite to each other, and then you put your sample that you need to study in between those diamond tips. So you can apply force mechanically.
Dias's team applied pressures almost as extreme as those found at the Earth's core. They did this by crushing the compound inside a microscopic niche they carved out of a diamond anvil. Then, they triggered chemical reactions with a laser beam.
So that way, we were able to really find the room temperature superconductor. It's under pressure, right? What we have found is under pressure. So somebody can argue that, okay, so you went from one extreme to another extreme. So So who cares? Or what's a big deal in that sense, right? But I think there was a time that we were, even the scientists were thinking that room temperature superconductivity is not possible. To be honest, the very first time when we saw this one, I didn't really believe it. And I was like, okay, this is too good to be true. And why we are seeing this nice resistance? Everybody around the world contact me via email or phone calls, and they were very excited. And this is a landmark discovery. But there are a lot of work to be done, because even though we know the initial composition, what are the material that we put together to pressurize it, but we don't know actually what it is really, what the sample is superconducting. So that those studies need to be done.
So for now, levitating trains, lossless power transmission, and perfect energy storage are still utopian dreams. But Diaz believes they're not far off.
I would say I'm very optimistic. Probably in the next 5 years or 10 years, may be able to get to a real application.
In 2006, an astronomer detected a brief and extremely powerful radio signal coming from a distant galaxy. Over the next few years, dozens more were observed. Astronomers traded wild theories trying to explain them. This year, a fast radio burst was observed again, but this time it came within our own galaxy. In just a millisecond, the source emitted 100 million times more power than the sun. Brian Metzger and his colleagues at Columbia University analyzed the data and found the source, a magnetar.
So a magnetar is a neutron star. So neutron stars form when massive stars die at the end of their lives. The core of the star collapses in and forms a neutron star, a very compact object about the mass of our sun, but the size of New York City. And then the outer layers of the star explode as a supernova. And so a neutron star is what's left over. And magnetar is an extreme version of a neutron star with a very strong magnetic field. So there was a magnetar in our own galaxy that produced a flare of X-rays, and arriving on Earth at essentially the same time as the X-rays was a burst of radio emission, which if we'd put it into a different distant galaxy would have looked a lot like a fast radio burst. But we were, identifying that it came from a magnetar within our own galaxy. So that's pretty good circumstantial evidence, that magnetars can produce fast radio bursts. Fast radio bursts are great because we can see them almost to the edge of the universe. And so in addition to actually understanding what's producing them, one of the exciting things is we can use them as probes of the state of matter between us and the radio source. And so I think that's very exciting as we discover more and more fast radio bursts. And if it turns out that they come from magnetars, then we're also probing where all the magnetars are. It turns out that they come from magnetars, then we're also probing where all the magnetars are in the whole universe, which is something we didn't think, would have ever been possible.
Breakfast that's ready in a snap. Lunches you actually
Not only astronomers, but also ordinary people experience incredible delight from all the novelties that the night sky broadcasts to us. Some consider it the highest romantic display of affection to give your beloved a star. But how should we react to such an unusual gift? To begin with, let's be a little more specific. What if it's Betelgeuse? If, during a date, a guy decided to demonstrate his knowledge of astronomy, During a date, a guy decided to demonstrate his knowledge of astronomy. Sorry for the spoiler. But most likely he'll point his finger at the brightest star and call it the Big Dipper. But one of the most famous and also one of the few stars which you can see so clearly with the naked eye. This is Betelgeuse. It's a red supergiant located in the right shoulder of the constellation Orion. Here, even the most skeptical girl will think, well, that's what I would like. Perhaps soon your interest will disappear though, because recently, researchers discovered that the star is beginning to fade. It seems to be nothing super interesting, but a star usually fades before it has a huge explosion. All astronomers are now in anticipation of the most colossal cosmic event. Throughout its history, humanity has never recorded the explosion of a star, at least not with telescopes. As early as the 1st century BC, Sima Qian and his treatise on celestial apparitions mentioned Betelgeuse. But at that time, all the researchers observed was a yellow glow, and by the 2nd century AD, based on the research of Ptolemy, it had turned red. Betelgeuse reincarnated not only in color, but also in speed, which has increased significantly to an incredible pace, about 5 kilometers per second, which is 4 times faster than that of our sun. The reason for this may be that Betelgeuse devoured its closest stellar neighbor, which was significantly inferior to it in size. In the world of space, Betelgeuse is clearly not a herbivore, and this planetary predator never ceases to amaze to this day. Just recently, scientists recorded the star's new trick. Betelgeuse started winking at us. Then the star began to hide from our eyes behind some dust. And this can mean only one thing. There's very little time left before the death of the Titan. Stars die in 2 ways. Either they fade away, or they generate a powerful explosion, and Betelgeuse is preparing for the latter. It can happen at any time, but on the astronomical scale, Betelgeuse will explode in the next 100,000 years, or in 2022. The explosion of a star so close will be a supernova phenomenon for our planet, and most importantly for science. The last time something like this was observed by our ancestors was in 1604. This explosion and formation of Kepler's supernova happened at a distance of 13,000 light years from Earth, which is 20 times the distance to Betelgeuse. Given the short lifespan of a person and the large-scale lifespan of a star, it can be said without exaggeration that you can catch such an event as the explosion of Betelgeuse once in never. When else will you be able to watch such a large-scale explosion without fear of death? After all, scientists suggest that Betelgeuse is too far away to have a significant impact on the Earth. But remember how astronomers miscalculated in forecasting a solar storm? It was supposed to destroy the Earth in 2012, but in the end we survived. But what if this time everything is the other way around? found that, assuming a happy ending, scientists haven't carefully considered the terrible scenario of events. Scientists have apparently forgotten that in the past, due to the explosion of stars, the Earth's temperature rose significantly. Add a pinch of global warming here, and it turns out we throw the planet into a hot frying pan. Also, the explosion will damage the ozone layer, which protects the Earth from harmful
How do I really feel about health insurance? This is pretty frustrating.
Health insurance to me was exhausting and expensive. That's when I found Sidecar Health.
Hello wonderful person, this is Anton, and today we're going to be talking about these incredible discoveries in regards to fundamental physics. And more specifically, we're actually going to be combining two different discoveries, which in a sense suggests that our understanding of fundamental physics is still not really perfect, because both discoveries suggest that something else is going on in the universe that we don't really understand. And what I'm actually going to be discussing is the very recent announcement from the Fermilab of the so-called G-2 experiment that has been confirmed officially to have something unusual going on in it, and also this completely other discovery from CERN in Switzerland, which also suggested something else going on with a completely different part. Particle in a completely different experiment. Both discoveries were made only approximately a week apart, and both to some extent are kind of groundbreaking, at least for the particle physicists. For us, for normal people, we still don't really know what all of this means. But, as always, let's start with the baby steps. So today, in modern physics, the so-called standard model of particle physics is probably the best model we have for the world around us. Basically, these 17 different subatomic particles you see right here more or less represent what we believe happens in the world around us, at least when it comes to particle interaction, with the idea known as QCD or quantum chromodynamics being responsible for explaining how all of these subatomic particles interact with one another. And over the years, over the past few decades really, a lot of different experiments conducted in various particle accelerators, for the most part, have been consistently proving this idea over and over. All of the theoretical predictions, such as for example the famous Higgs boson, were eventually confirmed by various experiments in, for example, CERN, inside the Large Hadron Collider located in Switzerland. Now, all of these experiments over the years, once again, allowed the scientists to quite confidently say that our understanding of the world, and specifically the standard model of physics, for the most part seemed to have been correct. But the model was obviously still not perfect. For example, it still didn't really explain very well how gravity works or how objects are able to attract each other. It also didn't really explain the mysteries of the universe, such as dark matter. But more importantly, there were some experiments that created the results that were kind of difficult to explain. And one such famous example from 1990s was what's known as the Brookhaven experiment, although according to Google, it's also some sort of a VR shooter game, which I don't think I'll ever be playing because it kind of looks scary. Anyway, that one experiment created a tiny problem for the particle physicists, which for the past few decades they've been kind of trying to figure out. But what exactly is this problem and why is it a problem? Well, it really has something to do with the predictions of one of these subatomic particles. And specifically this particle right here known as muon. As you can see, it's pretty much the cousin of electron, except that it's dramatically more massive, like 200 times more massive. But in every other respect, it is very similar to electron. As a matter of fact, other properties like spin and electric charge are exactly the same as an electron, so the only main difference here being the mass. And one of the main reasons we're not really as familiar with muons compared to electrons is actually because we haven't really found a practical use for them yet. Electrons are obviously used everywhere, that's how electricity works. But for muons, one of the only uses we have for them so far are, for example, various types of penetrating scanners, such as ground penetrating scanners, which muons can do much better than electrons, because they're basically more massive and can easily go through matter and thus detect objects much deeper in the ground. As a matter of fact, right now, as I'm speaking to you and as you're listening to me, or more specifically in the area around 1 square meter around you, about 10,000 muons go through that area every single minute. And the way that they form is through the interaction of cosmic rays coming from very powerful quasars, supernova, and a lot of other powerful objects out there with the upper atmosphere of planet Earth. And as these elements strike the upper atmosphere, the muons that are generated as a result go through pretty much everything, including you and including the ground underneath. And some of them can actually even go through the entire planet entirely. So muons are generally really good at penetrating things. And so over the years, the scientists have learned quite a lot about them, and one of the properties that is known to scientists about muons is that if you were to place them in the magnetic field, they would basically start spinning. And this spin itself is known as the G factor, with the G factor for muon being G-2. So next time you hear someone say muon G-2, that's basically what they're referring to. They're referring to this predicted value of a muon spinning inside the magnetic field. But it turns out that this value is actually not really 2, with the main reason being virtual particles predicted by the quantum physics. As these virtual particles start to appear everywhere, they actually interact with the spin of muons and end up increasing the value by just a little bit. So it's not really 2, it's more like 2.002331 and so on. And this value that you see right here was the predicted value from the most recent very thorough analysis from 2020 that was released by a lot of scientists working together. Now this is a mathematical prediction value, and it just so happens that that experiment I mentioned previously, the Brookhaven experiment, found this value to be a little bit different. Something wasn't really adding up. And so for the past few decades, the scientists in different labs were trying to recreate these results, with the Fermilab, whose video I'm using here, essentially even getting a completely new super powerful magnet just to study this effect, just to find out if there is something going on after all. And well, as you can probably imagine, after years and years of studies, they finally have the results. And the results, well, let me show you the picture to summarize this. The results sort of confirm the original Brookhaven result, and definitely go against the predicted model that was just confirmed last year. And even though the actual difference is really minuscule, the experimental results here don't really align with the standard model predictions. The difference is quite significant, which means that both experiments found some sort of an anomaly, suggesting either A, the 17 subatomic particles we have here do not necessarily explain the whole world around us. There might be some other 18th hidden particle that was just discovered. Or B, something completely different, something that nobody really understands yet, is happening to the spin of these muons, which might be some sort of fundamental discovery in regards to muons that nobody has ever made before. Either way, for the particle physicists, this is one of the biggest groundbreaking discoveries of the last 50 years. But to make sure that this is a real discovery and not some sort of fluke, because there is still a tiny chance that maybe this was a mistake, and specifically here we're talking about 1 in 3 million chance, the scientists are going to be conducting this experiment 5 times in total. And if after 5 times they still get the same results, well, in that case there's definitely something going on. And so in that sense, it's a discovery that doesn't have an explanation or even theory behind it. Nobody really knows what's happening here. But that's just one of the discoveries. Remember in the beginning I mentioned there were 2 discoveries? Well, the second one is completely unrelated, although maybe somewhat related. And by the way, check out the video from Fermilab if you would like to learn a little bit more detail about this discovery as well. But anyway, so Fermilab discovered one thing, but CERN in Switzerland discovered something entirely different and also unexplained. And in this case, it's kind of related to the main premise of the Large Hadron Collider, or basically its main purpose. Its main purpose is to study hadrons. It's to study the particles that are made out of elementary particles. So in this case, if we take one of the quarks, specifically an up quark, and if we combine it with a down quark and another down quark, we're going to
buy the new Pixel 5a with 5G and save $40 when you bundle it with Pixel Buds A series.
We're going to get a neutron. If we combine 2 up and 1 down quark, we're going to get a proton. Those are hadrons. Hadrons are basically the larger particles that are made from subatomic particles. But we don't have to combine 3 of them. What if we combine 1 up and 1 down? We still are going to get a hadron, but it's not going to be stable and it's actually going to fall apart, creating something entirely different. And so that's pretty much what CERN scientists have been doing for years and years and years now, and that's kind of the main purpose of the experiments there. They try to create hadrons, they try to destroy them, they try to collide them, and then try to see what happens. But a lot of this is also based on various theories, And many of these theories have been confirmed over and over and over again. And one of these theories is about this one hadron known as beauty meson. Okay, more terms. So this one is basically created from combining one down quark and one bottom anti-quark. So here we actually start using a little bit of antimatter. Although even here you can combine some other quarks to create slightly different beauty mesons. And just generally, to create a meson we need some sort of a quark and an anti-quark. But it cannot be the same anti-quark because then it just eliminates and creates energy. Anyway, long story short, the predicted model for these beauty mesons suggests that they do fall apart, creating an equal amount of electrons and once again muons. And more specifically, they should be producing an equal amount of electrons and positrons, or muons and anti-muons. And so here, if we were to take about 100 of these beauty mesons, with time, after only a few milliseconds, all of them should create approximately 50 electrons and approximately 50 muons. But as this paper that was recently released by certain scientists discovered, they don't. The data from this experiment suggests that a lot more electrons are produced compared to muons. And this once again suggests some sort of a problem with the theory, and very likely suggests some sort of an unusual, not well understood and possibly completely unknown to us physics at work. Something that many scientists will be studying for years to come. Now, it could be related to the previous muon discovery. Maybe muons are the actual culprits behind both of these discoveries, or maybe there is some sort of an unknown subatomic particle in existence. That absolutely no one understands just yet, but at the same time, the real answer is that nobody knows. And this is of course the beauty of these modern experiments. Today we've reached a point where the experiments are so advanced and are so precise that it's very difficult to argue with some of these discoveries afterwards. And if the scientists have detected something, and especially if they've done it several times, it might indeed suggest new physics at work. And because we haven't really changed the fundamental physics for about 50 years now, in some sense for particle physicists, this is a groundbreaking discovery. But for us, for the normies, for people that don't really do particle physics, well, we don't really know what to think of this just yet. I mean, like I mentioned before, we don't even use muons in real life just yet. We don't really know what they're used for or what they can be useful for. But if muons one day do become as important as electrons, maybe then we might appreciate these discoveries a little bit more. For now though, it is more or less theory only. We still don't really know where all of this will lead and if it's actually going to help us to explain the universe around us. Nevertheless, super exciting discoveries, very unusual how both discoveries happen around the same time, but hopefully in the next few years we'll know exactly what's happening here. Hello wonderful person, this is Anton, and today we're going to be discussing some new discoveries in regards to the magnetic field of planet Earth, and more specifically a discovery of a somewhat unusual and somewhat unexpected cycle that seems to change the magnetic field of our planet every 200 million years. while at the same time changing how the magnetic field seems to flip around the planet. And all of this also explains a few other mysteries, including one of the extinction events that happened a few 100 million years ago, that now the scientists believe very likely happened because of the magnetic field. So let's talk a little bit more about this, starting with the extinction event itself. So roughly around 360 million years ago, and for a period of a few million years, the Earth experienced one of the big 5 extinction events, this one known as the Late Devonian event. But it wasn't just a single event, it was actually several events that happened one after another, with each of them affecting different species and different types of species differently. And one of the more unusual and well-known victims of this extinction event was this strange-looking fish known as Tiktaalik. A fish that sort of looks like a mixture between a fish and a crocodile, and was very likely one of those fish that learned how to get out of the water and to possibly even walk on land. But what exactly caused these different extinctions during the period of several million years? Well, it seems like there was no one single event or one single source. As a matter of fact, this is one of those somewhat mysterious extinction events that was very difficult to explain until I guess more or less recently. And mostly because of this study and a few other ones that pointed out at something that nobody really noticed before. A lot of the fossils from this period, specifically fossils of various land plants, seem to have a lot of different UV damage, or even mutations caused by ultraviolet radiation. It's as if a lot of these plant spores were somehow damaged by the extremely high doses of UV radiation. And although it might suggest some sort of a supernova event or maybe some sort of a space-related event that might have happened not so far from the planet, a more likely explanation back then was actually the reduction of ozone layer and possibly even the reduction of the magnetic field itself. Which is exactly what some of the recent papers discovered as well. The magnetic field during this period was actually much lower than today, anywhere from half the strength up to about a quarter of the strength. Which sort of implies that back then Earth was not a very good place to live on, with most likely only deep oceans or maybe some caverns providing enough protection from all of this UV radiation. And specifically, a lot of studies analyzed the levels of mercury and a lot of other components in the fossils to establish that no other major event could have caused the extinction in this case. It could not have been some sort of a space event, and it most likely was not some sort of volcanic event either. It must have been the sun itself. And interestingly enough, all of this then resulted in a major ice age on the planet. This is sometimes referred to as the Karoo Ice Age. In this case, the loss of the ozone layer might have caused some of these climatic changes. But that's not something we're going to be discussing today. What we are discussing is one of these papers that established there seems to be a pattern and also some sort of a cycle planet Earth goes through every 200 million years. And a lot of the results from the study come from the investigation of various rocks and various deposits located right here in in Scotland. The paper in the description below provides the actual description for what each of these colors mean and what actual date they represent in the study. But in a nutshell, it represents the era between about 330 million years ago and approximately 416 million years ago. And the first unusual discovery was that the Earth's magnetic field back then was actually much weaker than it is today. Once again confirming that very likely this might have caused the extinction event and all of the damage from the UV light that we're observing in some of the samples. But we also know that the magnetic field and the magnetosphere shifts and changes all the time and even occasionally flips. Generally though, it's believed that in the last 83 million years, the planet went through approximately 180 different reversals or magnetic field flips. There's no actual explanation for why they happen and there's no real understanding behind them, but the samples from various rock deposits confirm that this happened many times, with the average time between flips being about 450,000 years, but the last magnetic flip occurring 780,000 years ago, meaning that we're kind of overdue for the next flip. But if we expand the timeline to several hundred million years, we'll start discovering something else really unusual about the way that the magnetic field behaved in the past. It's a little bit easier to see it on this timeline right here, with the stripes representing the flips. And so if we start going back in time, you'll notice something really unusual happening approximately 83 million years ago. We reach a period when there's actually not a lot of flipping. As a matter of fact, no flipping whatsoever for tens of millions of years. But then it returns to the flipping again. Yet, at the same time, in approximately 200 million years, it reaches the next long period where no flips occur and the magnetic field seems to be pointing in the same direction. We refer to these two events as supercrons, officially defined as a period when the magnetic field does not flip for over 10 million years. And the two most well-known supercrons are referred to as the Cretaceous Normal and Kaiman. And well, up until this paper right here, nobody really knew what exactly is happening during those supercrons and why the magnetic field sort of remains constant during that time, and at the same time why the magnetic field flips so much in between supercrons. But the new analysis from various ancient lava flows located in Scotland confirmed the original prediction from approximately 10 years ago. Our planet seems to have a 200 million year cycle when the magnetic field doesn't just flip, it also weakens and strengthens. And when it strengthens, the magnetic field does not flip at all. It creates what we refer to as the supercron, which can sometimes last for several tens of millions of years, which also means that during that period, our planet very likely is completely sheltered from a lot of different space radiation, or at least from the solar radiation and a lot of solar emissions. But in between the supercrons, we get the weakening of the field, and during the weakening, that's when the magnetic field starts to flip back and forth. Now, the actual mechanism is not well understood, but it seems to be directly correlated with the much weaker magnetic field on the planet, which means that by weakening the field, it somehow reduces the stability and forces the inner core to possibly change something on the inside and shift the magnetic field from north to south, from south to north. Now, like I said, we don't really understand the mechanism, but this is what's implied from the paper and from the analysis based on these rocks. And one of the more important discoveries here is the confirmation that whatever happened 330 to 400 million years ago, when the actual magnetic field dipped by quite a lot, seems to also happen exactly 120 million years ago. Once again suggesting that this is a cyclical event, and it very likely is going to repeat in a few million years from now. while at the same time suggesting that right before the superchron, when the magnetic field strengthens and sort of lasts in the same position for a very long time, the magnetic field weakens the most, which also implies that the magnetic field of the planet might start weakening more and more in the next few million years, eventually reaching very low levels like approximately 120 million years ago and approximately 360 million years ago. And so this unusual connection between the strength of the magnetosphere and the magnetic reversals is somewhat unexpected, but also somewhat important. This sort of connects a lot of different events, including the climatic changes, including the extinction events, to what seems to be a cyclical nature of the magnetosphere that once in a while seems to become weak enough to make the planet somewhat vulnerable. But naturally, we don't really understand a lot of these effects or what causes any of this. It's of course something related to the conditions and the interaction inside the planet, but what exactly happens we don't really understand. But in the next few years we might come closer to finally answering a lot of these questions and possibly being able to even predict some of these events in the future. For now though, all of this once again shows us how important the magnetic field of the planet is, and also how our planet seems to have quite a lot of undiscovered cycles, with some cycles being extremely important for the survival of the species on the planet. Although I guess for now that's all I wanted to mention. Check out the papers I mentioned in the description below, and check out some of the previous
Smash your quota every quarter with Vidyard. It's my go-to sales tool to—
You booked that meeting yet?
Hello wonderful person, this is Anton, and today we're going to be talking about another theory that tries to explain the potential origin of the mysterious dark matter. Where did it come from and what exactly is it made out of? And in this case we're going to be focusing on this very theoretical concept that proposes that the dark matter might actually after all be made out of tiny black holes. Although in this case the scientists behind the paper you can find in the description propose a relatively complex explanation involving a lot of particle physics and a lot of ideas from the changes in the early universe. But I figured it's still a pretty cool explanation, still a pretty good idea, pretty solid idea, and it's definitely something that I could try to explain in this video. And so the title of this paper is Primordial Black Holes from a Cosmic Phase Transition, the Collapse of Fermi Balls. And it tries to explain the mysterious dark matter as what's known as primordial black holes that existed since the beginning of the universe. Now first, quick side note, we still obviously have no idea what dark matter really is. We obviously see the effects of the mysterious dark matter, such as the expected versus observed rotation curves of various galaxies, along with some unexpected lensing effects from the invisible mass in the middle of different clusters that shouldn't really be there, with a lot of other observations we've discussed in some of the previous videos. But the problem here is that, well, for the past few decades, despite many different experiments, no particle has been discovered to try to explain all of this. For example, one of the most common theories uses what's known as WIMPs, weakly interactive massive particles, and this is supposed to be the explanation for how dark matter works, with the other common explanation being another particle known as axion. But though theoretically they do make sense, none of the experiments so far have found anything. No WIMPs or axions have been found, despite many different attempts to find them. And naturally, because of this, there are several alternative explanations to dark matter. The most popular, or I guess the most famous one, is known as MOND. But they don't explain everything. As a matter of fact, some things they cannot explain at all, and because of this, not everyone, or actually most scientists, do not accept them. The dark matter still is believed to be some sort of a particle, or maybe a tiny black hole. As a matter of fact, Stephen Hawking himself always believed that it was primordial black holes. Now there's a video from a couple of years ago where the Japanese scientists tried to investigate this idea, and they did so in a very clever way. They wanted to see if there are really these primordial black holes, or at least some sorts of black holes, traveling across the Andromeda Galaxy. And so they looked at the Andromeda Galaxy for a long period period of time, and they tried to discover any kind of signs of these primordial black holes by looking at the gravitational lensing effects of various invisible dense objects moving in front of different stars. Now, they've only found one, even though they expected thousands, and this implied to them that there were no massive black holes, or at least black holes in the range of the mass of our Sun, or possibly a few masses of Jupiter, traveling in the Andromeda Galaxy. Which also implied that the larger black holes could not explain dark matter. And normal black holes, the so-called stellar black holes, definitely cannot explain anything. You would have to have a lot of them everywhere, and we'll be able to see them in many different surveys we've already conducted. As a matter of fact, just in terms of the numbers of the stars in the galaxy, there are just not enough stars to produce all of these black holes. Nevertheless, primordial black holes could be entirely different. They would not be produced in the same way. They could be produced in an entirely different way, and they could also be a lot less massive and thus invisible, or at least somewhat invisible. And because of this, in that paper from the Japanese scientists, they also established that if there are primordial black holes, they have to be less than a mass of the moon or so, or possibly a mass of several asteroids. But I guess the question is, well, how would they be produced and what exactly could create such black holes? Well, there have been many propositions, but the one in this particular paper is particularly intriguing. And the explanation here involves what happened in the universe in the first moments after the Big Bang started. Essentially, the universe before a lot of particles became particles, before the fundamental forces solidified and became the forces we know today, and essentially when things were extremely different, the universe was extremely hot, and everything was extremely dense, extremely hot, and somewhat difficult to imagine. But we know that this probably existed in the first few moments, simply based on the observations from the CMB, the cosmic microwave background. And during that time there were a lot of different transitions and changes of state, as it's known. Essentially, as the universe cooled down, things changed into other things. And these changes of state can be sort of compared to how liquid water turns into ice, or how liquid water turns into gas. But in this case, today the physicists believe that the entire universe can be described in terms of different scalar fields. Fields of energy, fields of forces, and in each of those fields, various particles are produced through the breaking of symmetry. So essentially, in order to get a photon, or in order to get any particle, you would have to have certain field suddenly have some sort of a breaking of symmetry in order for the particle to be formed. Now, in this case, the scientists also are pretty certain that these fields transformed in their state, especially when the universe started to cool down. And during that transformation, it's very likely that some of the particles that used to be present in these fields might have also been somehow affected. And so this so-called phase transition is essentially what forms the idea behind this paper. They believe that the phase transition might have resulted in the formation of these primordial black holes. Here's how they kind of explain this. And so let's use an analogy here. The scalar field is going to be liquid water, or just an ocean in a sense. And in this case, our ocean is going to have its own particles that would not exist in modern universe. We're going to think of these particles as the tiny crystals of salt that are present everywhere in every ocean on the planet. And so we have the liquid ocean and we have the salt. Now normally on Earth, as the temperature increases, water turns into gas. But in this case, we're actually cooling down the universe, so it's slightly different. Anyway, as the universe was cooling down, a lot of these fields started to transition their state. They started to experience phase transition. And so in this case, the liquid water is going to be turning into gas. It's going to start evaporating. But just like with water, it doesn't just suddenly happen everywhere. When you boil water, it doesn't just entirely evaporate right away. It starts with tiny bubbles, and these bubbles start to kind of spread slowly, moving from one place to another, eventually combining, growing in size, and turning liquid water into water gas. But in our ocean water, what happens to the salt?
It's time to help people customize and save with Liberty Mutual.
Two kinds of people, Dad. The ones who have a B-bot, and the ones...
This medium-sized monster lives about 1,000 light-years away from Earth. That's almost 6,000 million miles. On the scale of the universe, it's right next door. More than 4 times the mass of our Sun, it's surrounded by streams of gas. One by one, gassy shreds send out the last flares of light before disappearing inside. And those are some of the brightest emissions in space. There are 2 stars nearby, one orbiting the powerful space object, and the other moving around this inner pair. Scientists think this newly discovered black hole might be the nearest to Earth. It's also the only system with a black hole visible to the unaided eye. Hey, good news! You're gonna visit it right now! Higher and higher into the atmosphere, and soon Earth turns into a glorious blue sphere. You pass by the International Space Station. Hi guys! But before you can see it in great detail, it's out of sight. No wonder. The largest human-made thing in space is traveling at a speed of more than 17,000 miles per hour. You move further from Earth and see numerous satellites circling the planet. They come in all shapes and sizes, but each one of them has an antenna and a power source, often a solar panel or battery. You reach the moon.
What is up guys, TechRax here. So today I got a really cool video for you guys. I've got the new iPhone 10. I actually just unwrapped it. You guys can see like this whole area, it's basically like barbed like this. The cool thing is I've got a rig where I'm gonna try and get this iPhone out once it falls already. I'm gonna use a fishing line to literally manually bring this back up. So if all goes well, this is gonna be a pretty cool video. So let's go ahead and get it started. So just to quickly summarize guys, what is going to go down? We got the iPhone 10, the fishing line. The phone is going to be attached to these 2 GoPro mounts and this adhesion as well. This is all wired together with this fishing line. So when the phone drops, this stuff starts rolling and rolling and rolling until it hits the bottom. So of course, if the mine hole is like over 3,000 feet deep, I don't think I'm going to start manually. Let's do this guys and see what happens. Everything is set up and ready to go. I got the mounts on the front and the back. Only the hole awaits. So I do want to record just in case. You never know what may happen. I'm going to turn on flash. Okay, let me double check. This is super nerve-wracking. Okay, let me go like this. Okay, I think this should be good. So in 3, hopefully you guys can see it. It's recording in 3, 2, 1. Well guys, so check this out. The line has completely straightened out 5 minutes later. And man, I don't know what to say guys. I really did not expect this to happen. I bought one of the biggest rolls at the store, like 2,000 feet for sure. And I guess this mine hole is even deeper. I don't see any light down there. The phone is probably just dangling. But we have to pull it out, guys. This might take me some time. I'm going to sit here and I'm literally going to be pulling on this until I get that phone. Yes, guys, finally I see it. I see it flashing. It's the little flashlight. Let me zoom in, guys. You gotta see this. Hold on. Man, I swear if this camera falls down this hole. Hold on. Can you see that flashing? That's the iPhone. And here we have our beautiful iPhone. Oh my goodness, this is all tangled up. Okay, yeah, this phone is completely wet. Let me check. Let me hit stop recording. So the back is a little bit dirty. Obviously there's no crack or anything, and that's pretty simple. The phone, it didn't completely fall. I do see a little bit of scuffs on the side right here. It might have hit the side of the wall, the rocks. But overall this phone did well, but it is wet. So it probably took maybe a little dip in water somewhere. And that wraps it up, guys. So thanks for watching. I think it was really cool to just see the journey of this iPhone 10. And I really actually want to come back here next time again soon and do this where it does hit the ground. And maybe do something, maybe you guys have any ideas to where there's less drag.